be moving in a circle. So that's the classical picture, but now in the quantum mechanical picture, you know, that orbit then becomes more of a kind of smushed out. It's more of a cloud. So we get a picture like this. So that would represent the electron in its lowest possible orbit, at least for the hydrogen atom. And then if we think about the next level where the electron could be, in the Bohr picture, again, it's an orbit, but it's just further out. So in the quantum mechanical picture, it's similar, except now there's another distribution further out, like this. And again, also in the Bohr picture, we label these different levels with the principal quantum number n. So we have the 1 right in there. And then when we go out a little further, it goes up. So n would be 2 out here. Okay, and then you keep going out further and further with your orbitals, and they just keep getting further and further away from the nucleus. I won't draw the whole thing, but like there'd be one out here, which would have its own little cloud, equals 3, etc. And we keep going further and further away. That's n equals 3. So those are quantum mechanical orbitals, but it's a little more complicated even than that, because as it turns out, when you get to this n equals 2, this second level here, there's more than just an orbital that looks sort of like a smushed out circular orbit. Okay, there is an orbital that looks like that. There's actually another one there at that same energy level as well, and it looks different. It doesn't have the same shape. So let me see if it kind of looks like a figure 8. Sometimes it's called a dumbbell shape, so it's right there like that, and it's the same size as the spherical shaped one, but it's got a different shape. So what we do is now we have to come up with different names for these different ones, like the one I wrote in black here, that's going to be referred to as an s orbital. You could think of s as standing for spherical. In blue here that I drew, okay, that's a different shape. That's called a p orbital. And there's actually 3 of them. The p orbitals, there's 3 of them at every level, and they go in different directions. So this one that I drew in right here kind of goes horizontally. And that one also is the same shape, but it's oriented differently. So it goes down there and up here, and that's another p orbital. So both of these are p orbitals. And then there's a third one that comes out of the board, or out of the whiteboard here, and it's also a p orbital. All 3 of those are p orbitals, and they all have in common that they have the same size. So they're all n equals 2 p orbitals, and so you can refer to them. Sometimes they'd be referred to as the 2p orbitals, or 2p. Sometimes you use the word subshell. Now n equals 1, if we go back to there, that doesn't have any p orbitals. It's just the way quantum mechanics works. The lowest level only has one shape of orbital, and that's the s. And when you go up a little bit higher, you get another s, but you also get a p orbital as well. And then when you go higher still, when you're at n equals 3, there's going to be s orbital, that s orbital there, which we've pictured already. There's also going to be p orbitals, and they're just bigger. They look like the one in blue, but they're bigger. But then there's a third type, and that's called a d orbital. Each time you go out a little further from the nucleus, you pick up another shape orbital, another type of orbital. Consider an energy level graph going up. So this one, I'm not only going to draw the energy level, but I'm going to label it and draw a little picture of it. So down here, that's the smallest orbital you could have, and we said that that's an s orbital. That's n equals 1, and it's also an s orbital. So you could kind of combine those two ideas and call it a 1s for that smallest one. And so that would be that spherical shaped one. I'm just going to kind of try to draw its picture with the nucleus in the middle there. Then we said we're a little higher in energy, or when we're at n equals 2, we also have an s orbital. And so we, again, just like before, we can combine that and call it a 2s. And that one's the same shape, it's just that it's a little bigger. Okay. So I'm drawing them as separate pictures, but you have to understand that they're on top of each other, and when they're actually in the atom, they're not separated like this. Now, for the next level, for the next type of orbital that I drew there, which was the p orbital, we know that that's also in the same. It's the same size. It's within the n equals 2 overall level, which is sometimes that's called a shell when you refer to the n level. So, but there's 3 of them. So what's sometimes done is to kind of make the picture a little simpler. I'm going to draw lines over here, 3 different lines. And notice I'm drawing them in the same energy as where the n equals 2 is. And we're still at n equals 2, but whereas this referred to that level right there, over here we're going to say that this is also n equals 2, but now these are going to be the p orbitals for n equals 2. And that's where we had those other shapes. So one of them went up and down like this, sort of a figure 8 shape or a dumbbell shape. One of them was this direction, and then the other one kind of came out of the board. That's kind of hard to draw, but I'll try to do the dotted line as going behind the whiteboard here. So those are 3 different p orbitals, but they're all at n equals 2. So this set here we could designate as 2p orbitals, and there's 3 of them. So this is what I meant by the 2p subshell. When we go up one more level, remember the next one's not quite as big of a gap as the first one. Now we're at n equals 3. Okay, and we can have another s orbital, but again, it's bigger than the others. Kind of hard to make it much bigger. And we're going to have p orbitals as well there. And then those will have their same shape, but again, bigger. Again, all of these are kind of on top of each other in the atom. Okay, so you have, this would be, this one over here would be the 3s orbital. All of these together would be the 3p orbitals, or the 3p subshell. Now with n equals 3, there's another shape that comes in, and it's kind of looks like a 4-leaf clover, or sometimes it's called a double dumbbell. And there's actually 5 of those. I'm going to move those up. I'm going to make them look a little bit higher here. But I would have to draw 5 lines for those. 1, 2, 3, 4, 5. Those are the d orbitals. This would correspond to the d subshell. Subshell. Oops. So let me see. Let me make sure I'm separating. So the 3p subshell is that one. These would be the d subshell, or the 3d subshell. And those, like I said, kind of look like a 4-leaf clover. They're like one might look like this. It has lobes here, and then another lobe down there, and another lobe down here. And there's 5 of those all together that are on top of each other. So it just gets a very, very complicated picture as you're going up in energy like this. So we want to be able to refer to these different orbitals without having to draw pictures, of course, or even draw energy levels like this. So one of the things that we can do is, besides having this quantum number n, this principal quantum number, the n equals 1, n equals 2, etc., like we've been doing, besides having that, we can also have another number, another quantum number to refer to these orbitals besides the letters. And so that's the L quantum number. So L is referred to as, well, it's the azimuthal quantum number, but L has different numbers for different letters. So L would equal a 0 for this one. So s orbitals have an L equals 0 value. P orbitals have an L equals 1 value. Whether it's 2p or 3p or whatever, L equals 1. So up here also, these would be L equals 1 for these p orbitals. So we have a n value and an L value. And then there's a third number that corresponds to how many of the different orbitals there are of that shape. And that's an M quantum number. It's a magnetic quantum number. So for down here, for the n equals 1, the s orbital has L equals 0, and then the magnetic quantum number is an M. And the M here is equal also to 0 for that energy level. But when L equals 1, M has 3 different values. It can be -1, it can be 0, and it can be +1. So it has 3 different possible values. Those 3 values, switch colors here, those 3 values correspond to the 3 different shapes that we have. Oops. I don't know why that color changed on me, but it's okay. So these 3 different shapes that I drew here before, one of them is m equals -1, 1, the m. There's a range for the m quantum number that tells you how many shapes you're going to have. And the range, m, takes on a range from -L all the way up to +L, with a 0 being in there as well. So since L was equal to -1 on our last example, that's why m goes from -1, 0 to +1. Because in that case, the L equals 1 was our p orbital, and there's 3 of them. We have the n quantum number, that's the principal quantum number. This designates the size of the orbital. Start at 0, starts at 1. It means the lowest principal quantum number in any atom would be n equals 1. And then you'd go up from there, n equals 2, n equals 3, 4, 5, etc. So that's the n quantum number. Then there's the L quantum number, and that designates the shape. L quantum number actually has a range as well. I didn't write it down yet, but L starts at 0, but it goes up in integers, but it can only go up to n-1. Can't go any higher than that. So remember that you have to also remember that for L equals 0, that's an s orbital, and L equals 1 is a p orbital, and L equals 2 is a d orbital, and L equals 3. I didn't show you that one yet, but that's called an f orbital. So you have s, p, d, and f, and they go up from there, but